Hello, college student. This video is for chapter 6.2, exponential function, part 3. So in this part, we're going to talk about compound interest formula. Compound interest, where money grows by compounding the interest, is a good example of exponential growth, and also is a good way to introduce something called continuous growth with a base called E, exponential constant E. We call it natural growth, natural exponent, I think, or exponential, natural. Okay, so let's start with compound interest. So we know if we put money into the bank, they will give us interest per compound per periodically. They credit it into the account. If we don't take it out, we just put it inside the same account. That particular additional amount will also get gain interest. So the formula that we can use to calculate such a growth is A of t, which is the amount in the account value in t years, and it's calculated by multiplying P, the principal or the present value, what you have right now, what you're investing right now, times a growth rate, the growth 1 plus the growth rate. So now the growth rate is given as a annual percentage rate. So the bank told you annually what the rate is, and you have to figure it out what that particular period rate is by dividing by n. N is the compound period in 1 year, number of compound periods in 1 year. So that means how many times the bank is going to credit money to you. So you would divide that into R that many times and then multiply by the total compounding period with n times t. T is measured in years. So if the bank is giving you like per quarter, so you have four interest compounding per year, then you would do the exponent for n times t. N times t. So this is how you do it. It's a lot of different variable that you plug in. Remember, P is the investment, R is the interest rate, N is the number of time you are to get the interest. So basically, if it is monthly, you will get interest every month. So in a year, then N is 12, right? If your compounding is quarterly, the bank is going to give you every quarter, so N is equal to 4. If you are to do a weekly, compounding, then your N in 1 year is 52 because that's 52 weeks. And if it's daily, you would say there's 365 days. Some bank use 360, but also do 365. Example 1. So this is just get used to that the formulas. An initial investment of 100,000, so that's P. 12% interest rate. So any rate that is quoted by a bank is annual interest rate. So this is R. You change it back into a decimal, 0.12. Compound monthly. So if you know compound monthly, then you would know N is equal to 12 because you're going to get 12 times of interest. So now use the formula. What will be the investment in 20 years? So you would say A is what would be 20 is equal to P 100,000 times 1 plus 0.12 over 12, right? Because it's 12. And then 12 times 20. So that means this is 240. So put everything in the calculator. Don't do any intermediate rounding. Actually, just do the whole thing in one shot. You can simplify this as 240 first. So you can do everything in one shot. So I'm going to do it. You can use a scientific calculator. 1, 2, 3, 100,000, right? 2, 3. Times open parenthesis 1 plus 0.12 divided by 12, close parenthesis to the power 240. So I got, I think I got right, I got that. Oh, so that's a lot of money. 1 billion, I guess. 1,089,255.37. So that's the final investment in 20 years. Okay. If the compounding is quarterly, what would be the investment in 20 years? If the compounding is quarterly, then I know N is the one that you need to figure out for. So my A also 20 is 100,000. 1 plus 0.12, but I'm dividing by 4, right? And then I do 4 times 20. That means 80. So enter this into your calculator. 120,000 times open parenthesis 1 plus 0.12 divided by 4 close parenthesis to the power 80. So 106,4089.06. So it's still over a million, but it's a little less because your compounding is less frequent. If you compound more frequently, you will get more money, right? So you would expect if you compound daily, you'll get more money. One more, which is to figure out what you will have if you are to save. This is your future value, your target, right? This is not your present. This is your target. You are to save this in 3 years, maybe for college or something. So you invest in an account that pays 6%. So R is 0.06. Compound semi-annually. That means N is 2. You only get your interest twice a year. How much would the invest? How much would the student invest now? So 40,000 is your final, is your A. You go to P. How much should you invest now? So that's present value times 1 plus 0.06 over 2. Okay, 2. And then 2 times what? 3. 3 years. So N is 2, T is 3, so this is to the 6. So we would have 40,000 is equal to P. Maybe we can simplify it. 1 plus 0.03 because this is totally simplified to the 6. So P would equal to 40,000 divided by 1.03 to the 6. So we can calculate P equal to, put in the calculator, 40,000 divided by 1.03 to the power 6. 1.036. Okay. So the present value that you should save is 33499.37. And if you do this kind of compounding twice a year and also getting 6% interest, at the end of 3 years, you would have 40,000. So that's how you solve this compound interest situation. And you notice that earlier we say the more frequent you have, the more what is it called? The more money you will have, right? So can I do it continuously without like every second or every tenth of a second? Just give me the interest every second. So we can do this, and you can see that it would amount to. Okay, so let's analyze this. A is equal to P 1 plus R over N, and then N times T. So this would be very big, infinity, and I have here infinity. So what would happen is if you do this, you would run into a number called an irrational number called E. So this number is called E, exponential constant. And you can model this by writing, instead of dividing by a big number, which is like 1/10 of a second, give me the interest. It will be P E to the R will move outside, become R times T. So this ray become a continuous ray. It used to be a like the growth rate per period. Now it become a continuous rate. And this number 1 plus 1 over n to the n would increase without bound. Oh no, it would not increase without, n would increase without bound, but this number approaches a value that cannot be written as a fraction. It is, but you can approximate it as 2.717282. And your calculator is there is a e to the something. Okay, there's a e to the x in the calculator. You can calculate this number. So if you calculate e to the 1, you'll see this. I can actually do e to the 15. Remember, e is not a variable. It's actually a number that comes out if you do 1 plus 1 over 1 million to the power 1 million. You'll see that it is like that. So if I use my calculator, e to the 1.5, so that would be 4.4817. Let's round to 4 decimal. I can also do an exponent to the power, oh gosh, e to the negative 0.11. You can do negative exponent because that's just 1 over something. It's reciprocal, 0.8958. So learn how to do this in your calculator. So they are a valid number that you can use. And it turns out that we can use E as a base when you are doing continuous compounding. So, or continuous growth. So lesson learned here is continuous growth corresponds to use E as the base. And then your in the past, your R is inside have 1 plus to get B. Now your R is called the continuous growth rate. Continuous growth rate. Now this is different from the growth rate that we have for 1 plus B. For money, this is the same rate, but it is different growth rate. But it is called continuous growth rate, which is different from the normal growth rate of 1 plus B. So maybe I'll talk about this continuous growth in the next video because I don't think I can finish this in 3 minutes.